Hi, I'm Carlton Coffrin.
And I am Lina Roald. And in this last video on convex relaxations in power system optimization, we are going to take you through some tips for using and developing relaxations of the AC optimal power flow problem. Okay, so I will start out talking a little bit about what are good uses of convex relaxations, like what can they give to you. So if you use a convex relaxation on their own, one of the things that a convex relaxation can help you do is to prove that a problem is infeasible, meaning that there is no solution to the problem. So this is something, if you have a non-convex problem, it can be very hard to prove, because if your solver finds that the problem is infeasible, it could be that you were just in a locally infeasible point. So therefore, the convex relaxation can really help you show that the total problem as such is infeasible.
And I'll note that a common use that I use for this is when I'm trying to debug my formulations, my non-convex formulations. I'll often make a relaxation of them and then test if that relaxation is infeasible. And it helps me determine if my data is incorrect, if my modeling is incorrect, or if the data I'm given is actually the problem and not the formulation.
Mm-hmm. Okay, so one of the next things you can do with this is to show that the solution is globally optimal. And there are kind of two ways in which this can happen using convex relaxation. So first of all, you can solve the problem by replacing your non-convex constraint by a convex relaxation. And then when you have that solution, you can check if it is actually feasible for the original problem. And if that is true, you know that the solution you have obtained is a globally optimal solution. The other case, which can help, where you can use a convex relaxation to help you prove that a solution is globally optimal, I mean, it would be the case where you find that a solution obtained for your non-convex problem has a zero optimality gap. So you could show that the objective value of a local solution to the non-convex problem has the same objective value as the solution you obtain with the convex relaxation. And here, a note of caution is that although the objective value might be the same, the solution to the problem, the actual value of the optimization variables might be different. So you should always make sure to use the solution from the non-convex problem, or that the solution that is guaranteed to be actually AC feasible.
Yeah, the assignments of the variables in the convex relaxation may not have anything to do with the feasible solution variables, even if they are zero optimality gap in the objective functions.
Mm-hmm. So a third thing you can do with a convex relaxation is to demonstrate that the problem is relatively easy to solve. So although we have this problem that is non-convex and kind of hard, it could be that if you are able to show that, for example, an SDP relaxation always finds a feasible solution, that would sort of be a proof that the original problem is also easy in itself. Okay, so this is kind of using a convex relaxation on their own. Other uses would be in combination with other algorithms, or in particular using also these local solvers where you solve the non-convex problem and kind of letting them help each other. So one thing you can do here with the relaxation is to provide a lower bound on the objective value for the feasible solution. So we have seen that we were talking about the zero optimality gap before. Now you can also think of a case where you have a solution to the non-convex problem which has a certain objective value, and then you solve the convex relaxation and you get that the optimality gap is not zero, but it is small enough that you don't really care. And for this you can either solve the convex relaxation using a one-shot optimization problem, or you can do sort of a branch and bound or spatial branch and bound where you are using global optimization techniques that will also frequently use this type of results. Okay, so the next thing you can use a convex relaxation for is to find a starting point for a local solver. So for example, you can solve the relaxation, take the solution, feed it into an interior point method, and use that to try and find a feasible solution that is sort of close by the solution obtained with the convex relaxation. And you can also use convex relaxation to compute stronger bounds on the decision variables, which is different from kind of trying to bound the objective value. Instead of bounding the objective, you will try to bound how far, like what are the ranges the decision variables can take on in this problem. So there you can also use convex relaxation for this. So these are examples of things you could use convex relaxations for, where the relaxations are giving you you have proofs that they will provide certain criteria for the solutions that you obtain. We would also like to include some kind of notes of caution for what are dangerous uses of convex relaxations, because we sometimes observe that people are using them as a replacement for the full AC power flow constraints without actually being aware that you might end up with infeasible solution in that way. So really kind of the first thing here is that if you are just replacing your original problem with a relaxation and you assume that it will always provide feasible solution, this can be really dangerous. So if you are, for example, replacing the AC optimal power flow with the STP relaxation, in many cases you might obtain a feasible solution doing that, but in many cases you might also not. And you need to be very cautious about this. And in particular, you probably cannot, it can be hard to make claims about this in general.
So one thing I see a lot is that someone will make a substitution like this, and then they'll test on 2 or 3 cases, which are maybe not coming from industry, and then they'll say, oh yeah, therefore this will work everywhere. And it's just not a very strong claim.
Yeah. Another thing is if you take a convex relaxation and use it in sort of a more complex optimization framework, so that could be, for example, a multi-stage problem, it could be a problem where you use decomposition, it could be a stochastic problem, a robust problem. And what some people do here is that they would maybe replace the non-convex subproblem with a convex relaxation. And the really nice thing about this is that then you can use algorithms that leverage the convexity of this convex relaxation. So many of those decomposition algorithms or robust algorithms to solve robust optimization problems really use convexity as a key component.
Yeah, the proofs that those algorithms say converge to the optimal require the subproblem to be convex. So it's very tempting to just say, okay, well, I'll make my subproblem convex, but this can actually lead to significant issues. You're not solving the same problem anymore.
Yeah, in particular, you don't have any, since you have no guarantees on your original problem in this case. So, and it can be sometimes harder. You might get guarantees on lower bounds again if you use it correctly. In many cases, this can be very useful to know that, if you use a relaxation as a subproblem, at least if you do it in the right way, you might know that the objective value of the full problem in the end will be a lower bound to the true non-convex problem. But yeah, there is a real need to use caution over here. And I will just make a little example of this in the context of robust optimization problems. So here we are back to our squiggly AC feasible space. Now think about the case that here, okay, let's say you were going to use a relaxation around it. So let's say the relaxation would look like this. And what you want to do when you have this robust problem is that you might have an uncertainty set that you want to make sure that every point in that uncertainty set will remain within this relaxation. So let's just say that you will find this, what you do is you sort of forget about the non-convex AC feasible space for the moment. And what you want to check is just that this uncertainty set is within the relaxation. It is all of the points in this uncertainty set is feasible. And when you have a robust algorithm, in some cases what you can do is that you can check that the corner points of your uncertainty set will be within the feasible set, and then you are able to guarantee that the entire uncertainty set is actually going to be feasible. So what you see here is that, okay, we are shown now that all of those little green points, they are within this relaxation, and they are all feasible, so we know that the entire green uncertainty sets are feasible for the relaxation. So this is a powerful thing to be able to do, and is something that you get because the relaxation is convex. The problem, of course, now is that if we replace the relaxation by the true AC feasible set again, what we can observe is that, first of all, some of those green little dots might no longer be inside of the feasible space. And then also it can be that even though those points are inside the feasible space, there might be sort of connections between them that belong to the uncertainty set we want to consider that are no longer feasible. So this is where it becomes sort of, you might think that you got a solution that is feasible, although all those, as soon as those green points at the corners were feasible, but that is actually no longer guaranteed because our true non-convex problem is non-convex.
And I think this example is really getting to the heart of convexity, right? Any linear combinations of points in a convex set will be obviously within that convex set, but when you have non-convexities, lots of these properties are out the window, and it becomes much, much harder to certify things like every interpolation between some points is also feasible.
Yeah, and that is why it is so, part of why it is so tempting to use those to use a convex relaxation to get back to those algorithms that require convexity. But it is really dangerous to do that if you are really looking to find true guarantees on robustness and on feasibility.
So I'm going to talk a little bit about common issues that you run into when you're using relaxations, and try to give you a bit of an intuition about when they can crop up and why it can be a pain. So we've talked in previous lectures about how relaxations can throw away power on the power lines, so that it can increase the amount of losses that you have on the lines. And at first glance, this seems like not too bad a property, because you wouldn't imagine making an optimization problem where this would be an advantageous thing. But I'll give you a couple examples where it can be very unexpectedly advantageous. So the first one is when you're trying to model generators with a non-zero output lower bound. So a lot of generators kind of either they're off entirely, or they're running at, say, 10 megawatts to 100 megawatts. So they have this non-zero lower bound on their output, and there's a discontinuity between when they're on and when they're off in terms of what the output can be. Now, it's interesting to observe that if you can throw away power on a power line for one of these generators, you basically never have to figure out if you can disconnect it or not. It's equivalent to kind of saying all the generators in the network have a lower bound of 0 on their output, because you can just set the output to their minimum value, say 10 megawatts, and then throw away that 10 megawatts on a line and kind of ignore the fact that you would normally have to decommit them in that type of scenario. Another example which can be quite interesting is when you have shunt elements in your network. So these are kind of like an example where you could have an injection into the network that you're not controlling. So normally we control, say, the injection through the generator variables, but these shunts they have an injection based on the voltage. Assuming that our voltages kind of range between some positive lower bound like 0.9 and 1.1, then there's no way of kind of removing this YS component of the power balance at every node in a bus. So this means that power is being injected by this, it can be consumed or injected. It depends on the sign of the YS term. But let's just assume it was injected and you had no way of satisfying that, or you had no consumer of this power that was getting injected into the system. This could be an infeasible case for an AC power flow problem, because you're injecting power, but there's no one to take it away. And so the thing that's interesting here is that if you put it into a AC optimization, it's going to say infeasible. But when you take a convex relaxation of this, it's going to say, sure, that's feasible, because it will just throw away the power injected by the shunt on the lines. So this can be a very subtle thing, which can be very hard to tease out, because it's a case when the relaxations will not help you prove infeasibility of this particular type of case.
Yeah, and it kind of also comes to the heart of this thing that there is a difference between when the non-convex problem becomes infeasible and when the relaxation becomes infeasible, because they are generally not the same. Right?
Yeah. Another common issue has to do with penalizing the objective function. So in a previous lecture, we've talked about how modifying the objective function can be very effective in encouraging a convex relaxation to be a feasible solution. So this can work very, very well in practice, but it does have limited guarantees. There are developing a general approach which can set these penalty parameters inside the objective function to encourage feasibility can be very challenging. There are results on combinatorial optimization problems which say that setting these penalty terms is just as hard as solving the original non-convex problem. So if you're trying to claim that the penalization method you have is going to be effective all the time, you should be a little bit cautious about how strong that claim can be. Another important note about this is that one approach that often happens with these penalization terms is you solve the convex relaxation multiple times. So you solve it with no penalties, you observe it's not feasible, you assign some penalties by looking at the solution, you solve it again, you see it's closer to feasibility but not quite feasible, you add some more penalties, and you iterate like this. So solving a convex relaxation is often comparable or slower than solving the original nonlinear problem to a local solution. So if your algorithm requires you to solve a convex relaxation many times to adjust these penalty terms, it could actually be much, much slower than solving the original non-convex problem and just converging to a local solution with no particular guarantees.
Yeah. And I think that is also an interesting thing to note here, that as far as we observe, sometimes local solvers, they can be very fast, where convex relaxation can be very slow. So in general, although we have also been talking before about these classes of NP hard problems and problems that are in P, there is a practical side to this where we actually see that solving a non-convex problem, although theoretically can be very hard, in practice can be very fast and can be sometimes much faster than solving convex relaxation. So that is also important to keep in mind when you have to make a choice of whether you are going to use a convex relaxation or just incorporate the non-convex problem directly.
Yeah, and I would also note that it's very natural that a convex relaxation would be slower than a non-convex optimization that only is striving for local optimality and not global optimality. And the reason there is that a convex solver has to converge to a globally optimal solution. It needs to kind of work its way all the way down until it's proven that it has a globally optimal point, where a local solver just kind of goes down towards a good solution, and as soon as it finds one, it says, yep, I'm done. And so it's only trying to strive for a local optimality guarantee, which is a much lower burden than a global optimality guarantee. So let's talk a little bit about my recommendations for best practices using convex relaxations. I would highly recommend keeping things simple and kind of increasing the complexity of your relaxation method incrementally. So here's a list of different relaxation methods, kind of in increasing implementation difficulty. So you have things like the copper plate relaxation, the network flow, the second order cone or branch flow, which we discussed in a previous lecture, and then it goes up and things get harder and more complex to implement. There are some special cases where you may want to jump directly to one of these, like the copper plate and network flow relaxations are extremely high performance. So if you're going to be solving thousands of relaxations, you probably want to go in that direction. If your algorithm has strong feasibility requirements and you really need feasible solutions, both the moment hierarchy and sum of squared methods are the only ones I know of where you can keep increasing their complexity until you kind of guarantee feasibility. But I will note that in my experience, this simple nonlinear second order cone relaxation can get you a long way. So I usually start with something like this, and then I measure the optimality gaps and I see if there's a need to go to something more complex before jumping in to something harder than this.
So you would say that in your experience, although the copper plate and network flow relaxations, and we should maybe say that here, that the copper plate and the network flow relaxations that Carden is mentioning here are really relaxations, and they are different from some copper plate and network flow approximations that you might think of when you hear those words. So, but those relaxations, they frequently will not give you feasible solutions, whereas this moment hierarchy SOS methods, they are much heavier, but they will typically give you feasible solutions. So what you are saying here is that in your experience, the SOC is kind of a typically good trade-off between getting something that is close to sort of giving you a good optimality gap while being also relatively easy to compute.
Yes. And that has to do a lot with just the state of algorithms of different classes of problems. The simpler the optimization problem, the more decades of research has been put into them, and the more mature the algorithms are that can solve those. So I'll note that semi-definite programming, which is a very popular method in power systems these days, is still very much an active area of research in algorithms. And so those methods, sometimes you run into difficulties with numeric stability because you're using academic codes. It can take, they're improving all the time, so that's like a very big reality of trying to solve these, where the simpler methods, like with second order cone, the solvers are readily available, they have a lot of industrial backing behind them, and they're used in real world scenarios a lot, so they're more robust in kind of the engineering sense of robustness.
Yeah. But that might change over time.
Yes, the decade from now, SDP may be much more mature than it is, and it might be a lot much easier to use than it is now. Mm-hmm. So an interesting point here is that it's important that you realize you need to prove properties, or at least make very strong analytical arguments or empirical arguments for things that you want to claim in about relaxations. So one thing that's very common is you see some results and you believe that your method has a strong property. So for example, the relaxation will always find a feasible solution, or the relaxation will always have a very small optimality gap. And it's important to note that you really need to quantify this either by going out and proving, like developing a mathematical analytical proof that will bound this in the worst case or will show that this always occurs, or going and doing an empirical study on where you benchmark on lots of cases. Now, I am generally not the kind of person who's doing analytical proofs, so I'm usually in the case of doing these benchmarking studies, and in that area I would emphasize that it's really important to test on many test cases, and actually the more examples you provide where your method is effective, the stronger your claim can be that it'll probably work in practice. But it's also important to take a look at the data quality of the cases you're testing. Are they coming from industry? Are they kind of toy academic cases? Were they made up by a PhD student 10 years ago just for some random example? And so it's important to think about that. It's also important to consider problem size. Will the method continue to have the same properties as you get up to, say, an industrial scale of problem? And so one of the efforts that I've been doing to help my research is developing a power grid library where we can kind of collectively curate test cases for benchmarking these things at a range of sizes where the community can try to vet them and say, yeah, this data quality is good. Because if you want to make really strong claims and you can't prove it analytically, you need a common shared library where everyone has agreed this is kind of realistic.
Yeah, and also to note there for this power grid library, as far as I know, there is also available results for a lot of kind of common relaxations that have been tested on this power grid library that you can find also on this website. So if you don't want to go through the entire kind of implementing all of this by yourself, I mean, there are also results that are there that have been provided for those test cases specifically. And if you can show that your method is doing better than all of those on these test cases, then you are kind of already pretty good along. Yep. Is that correct, Carlton?
Yeah.
Yeah, maybe also here, just a note, we have talked about this before, about proving that a relaxation is actually a relaxation. So if you make a change to, for example, an existing relaxation, or you develop a new relaxation that always finds a feasible solution, you should also be very careful that you have made sure that your relaxation can never cut off any feasible solution, because that is what a relaxation is. So if you develop a relaxation that adds, for example, on top of an existing relaxation, an inequality, you have to show that that inequality, or whatever you add to it, is always not going to cut off anything feasible from the original problem. Just to mention that when we are talking about proving.
Yeah, these are all important points. Relaxations require proofs. Approximations do not. So you can just do whatever you want in an approximation. So I'll just go through a couple of kind of standard algorithms that you might build using relaxations. So we talked about the benefits of standalone or hybrid algorithms. We've also talked in these lectures about this idea of finding an AC feasible solution and also finding a relaxed solution and then comparing them to generate an optimality gap. So this type of workflow is very common. You use some kind of heuristic, like an AC optimal power flow problem using a nonlinear programming solver to find a feasible solution to your problem of interest. And then you use a relaxation to provide a lower bound. So you have your base case network, then you solve it in two different solvers, and then you combine the results afterwards to basically say you have an AC feasible solution and it has a bounded objective quality. So basically on the lower side, it always converges and you always get a lower bound if the problem is feasible. And in the upper side, you're kind of just hoping that it converges to a reasonable solution or that it converges at all. It may converge and say, no, I wasn't able to find a solution, and then you're kind of out of luck at that point. But this is a common workflow, and my experience has been that the AC solvers, the exact solvers tend to converge, so this can be a very effective workflow.
Yeah, and I think it's also worthwhile to note here that we have observed that the AC solvers typically tend to converge to global optimal points. Is that?
I would say in the academic cases, that's the current observation, but it's not well understood if that's a data quality issue or if that's a more fundamental mathematical property.
But I think it is also worthwhile to note here that your AC solver and your relaxation, they might have an optimality gap that is non-zero, and it could still be, in that case, that your AC solver actually has found the global optimum. It might be that that is the best you can do in terms of finding a feasible solution. So you cannot really say in the case where there is an optimality gap, there is more work involved in understanding where does that optimality gap come from. Is that because the AC solver has found a local optimum, or is it because the relaxation is not tight? That is something that you have to figure out.
Yeah, and that's one of the reasons why we're always pushing on both sides, you know, to see if you can improve the feasible solution or to see if you can improve the relaxation, because with a gap, it's not obvious which is the problem.
Yeah.
Another one of these kind of standard relaxation or workflows using relaxations is a kind of bootstrapping approach where you can solve a relaxation to provide some insight into a more general problem. So you're going to solve your relaxation, you're going to hope that it provides kind of a good assignment of some of the decision variables or a good starting point for a non-convex solver, and then you're going to try to either recover an AC feasible solution with an AC optimal power flow or an AC power flow solver. So basically the workflow here is that you take the base case, you put it into your relaxed solver, then you use the solution from the relaxation to bootstrap some kind of non-convex solver, and then if that converges, now you've got a feasible solution.
Yeah.
Okay, so another interesting use of relaxations is for bounding parameters of your problem. We talked about that at the beginning of the lecture, so we'll just show you an example. So imagine you had a question like, what is the biggest angle difference on some branch in your power network? And you have a fixed demand profile, but the generators can kind of vary any way they want. So basically you're thinking about, for all the possible generator dispatches, how big could the angle on this line get? And you may be curious about that for stability reasons, or just kind of because you're curious how heavily loaded that line could get. And this is kind of how you can formulate that question. This was the original non-convex AC problem we wanted to solve. Instead of minimizing fuel cost, now we have a new objective, which is to kind of like minimize the biggest difference of these two angles, which is the same as maximizing how wide they are. So basically you're going to make the angle as big as it can possibly be. Now this problem isn't any easier to solve than the original AC OPF problem, so maybe it would be difficult to answer this question, so we don't want to solve that problem, but we can replace it with a relaxation which is easy to solve computationally. So here, we're exploiting the property that relaxations are always providing us an optimistic objective value. So if I set the objective to be some quantity of interest to me about the power network, it'll give me an optimistic value, and that provides a bound on what it could be in the real AC problem.
So what you're saying here is it's sort of safe to assume that the angle difference in the original problem will not be larger than what you find with this parameter bounding.
Correct. And it's worthwhile noting that if, for whatever reason, you want a pessimistic bound on what this value could be, you want to use one of those restrictions that we've touched on in previous videos.
And that being said, that is a very challenging thing to find, a restriction. And there's only very recent results that actually provide this kind of things, and it's still under development.
Right. And then just as a point of contrast, approximations provide no particular guarantees on what their objective value is. So this is a good example of where some type of analysis where relaxation or restriction provides you some clear, quantifiable result, where approximation is just a guess.
Mm-hmm. Okay, so we could also think about this in a slightly different setting. So instead of, as Colin mentioned before, having a fixed demand profile and trying to find out like what are the largest angle differences we can see in this problem, we could sort of turn it around a little bit and say like, okay, what if we had uncertain demand, for example, because we have a lot of rooftop solar PV in our system. What is the largest impact this uncertainty in the demand could have of any of our constraints? So this would be kind of getting at being able to sort of provide for a given solution robust feasibility guarantees. So let's say, for example, we are trying to solve the problem that we see here. So in this problem, it's worthwhile to note that we would like to try to maximize the power flow on the transmission line between node I and node J. So this is different from the objective that we typically see in this optimal power flow problem. But what we really would want to find here is to see, can we force this power flow to go beyond the limit that we had originally in the problem by changing the demand profile. So our objective variable, our optimization variable here is no longer the generation from the generators, but rather we are trying to find the worst case demand within an uncertainty set U. So the worst case demand can be anywhere within that set, and we want to find that the demand that is able to maximize this power flow. And here it's also worthwhile to note that we have included a constraint on the generators that is representing the automatic generation control. So essentially what would happen if we have already fixed sort of our generators, which would be this SG0 variable here. And then we would have this kind of participation factor where the generators, according to their participation factors, are adjusting relative to the changes in demand. And then at the bottom here, we have these AC power flow equations as we have seen them before. So let's say we want to try and solve this problem in order to see if our SG0 solution is able to provide us the guarantees that we want on solution feasibility when our demand is fluctuating. So again, we have this problem here, that this problem with the AC power flow constraint is really kind of too hard to solve. It is hard to find to find a solution to this problem. So instead, we would rather like to replace those AC constraints with a relaxation. And here it is really important to note that the reason we want to do this is that, as we saw before, the relaxations provide an optimistic objective bound. So really, we are getting sort of a too high power flow in this case. You could imagine that the estimate that we are getting by trying to maximize the power flow on this line would be larger with the relaxation than it would be with the AC, the original AC power flow constraint. And that is exactly what we want to know here, because we want to have some conservative estimate. And then also we should note here that you should take with caution that the relaxation or the worst case demand that we obtain when we solve this problem for the relaxation is not necessarily the correct worst case demand. It could be that it's a different combination of demands that would be even worse for this original AC power flow constraints. So also one thing I would like to note when we are looking at this problem is that here is one good example of a case where we are changing the objective in a way that could sort of make the relaxation become less tight or less give us less good bounds on the objective, because here you are seeing we are really trying to maximize the power flow on a line. And if you have been following all of those videos we have had here, you have seen several times that one of the places where the relaxations are typically able to cheat is when we is that they are able to throw away power on the line. So here you could imagine that the relaxations would really want to push more power into the line because it's trying to maximize the power that goes into it. So it could happen in this case that if you don't use the right kind of relaxation, you would get a very conservative estimate of the uncertainty impact that is nowhere close to being real.
Yeah.
Okay, so...
Great. Well, congratulations. You have come to the end of our series on convex relaxations in AC power flow. At this point, I think we all deserve some relaxation on a beach in a hammock. That would be very nice. And so thank you very much, and we really hope you enjoyed these lectures.
Yeah, we hope you have learned something from this. We hope you will this will serve as a good starting point for you to go out and read more on the literature on this relaxation, and it will help you apply them in your work in a good way. We are really looking forward to follow whatever work you will be doing on that. So enjoy the relaxations and the power they are giving to you.
Yay! We'll also plug that we have some bonus materials coming after this lecture, where we'll talk about some more exciting applications of convex relaxations in a bit more detail.
Yes. Okay, thank you all.
Thank you.